Okay, so at this point, we've done our lab. Parts one and two had to do with like which variables affect resistance. And we already figured out that length and resistance are linearly related. Ideally, if you were measuring this, as length increases, resistance would increase. In the lab, you don't get an exact relationship, an exact direct relationship. That's just because your meter itself has some internal resistance. In general, the direct relationship that occurs because the longer wire you have means that there's more atoms for the electrons to bump into. And every atom that it interacts with slows the electrons down. So a longer wire means more interactions between the electrons and atoms, so the more resistance those electrons face. Our graph for length versus resistance was supposed to be direct. Yours was linear because there was an internal resistance from the multimeter. So ideally, we should have some sort of thing where like resistance increases so length increases and vice versa. That's why when we ultimately get our resistance equation, length will be in the numerator. Right? But let's talk about part two. In part two, you saw Mr. Lubin taking the wire and folding it over itself. Well, every time he takes that area and increases it, it's kind of like giving more space in a crowded hallway. Increasing the area actually makes it easier for electrons to travel through. This is an inverse relationship. So as area increases, imagine I'm a wizard and I'm able to like take the lockers in the hallway and move them farther apart. That makes it easier for our student electrons to walk through. A wider area makes it easier for electrons to go through, so the resistance decreases. So graph for area versus resistance should be an inverse. It's not really an inverse square. Inverse square is things where like the electrons would like spread out evenly in a sphere over space, and that's not really what's going on here. Making the area bigger and bigger gives more room for the electrons to move, so the resistance is smaller. You can imagine like 1,000 people trying to get out of the cafeteria really fast. If you opened a second door, they'd be able to flow out faster because there'd be more space, more paths, more options. And that's why, with the inverse relationship, the area ends up being in the denominator of our resistance equation. Which leaves the last part. We know that the resistance depends on the material. If I replaced nichrome or graphite with silver or rubber, I'd get drastically different results. So there must be some other variable that has to do with material. And we named this material constant. We call it resistivity. Its symbol is a rho, a lowercase Greek letter rho. Its unit is the ohm meter. It's actually ohms times meters. And resistivity is a measure of a material. It tells you how well does that material, like silver in general, copper in general, nichrome in general, like how good of a conductor or insulator is it? A large resistivity, like rubber has a resistivity that would be in like the millions, right? A large resistivity means it's really good at resisting the flow of current. So a large resistivity must be a good insulator. A low resistivity, like silver, look how small the silver resistivity is, right? 10 to the negative eighth. Silver's resistivity is so darn small because silver is such a good conductor. You guys were measuring the resistivity of nichrome, which will end up being something like 1.5 times 10 to the negative sixth, if I correct powers of 10 in this chart. Right? All of the nichrome in the world has the same resistivity. All the aluminum in the world has the same resistivity at 20C. Right? Resistivity is a property of the material in general, but resistance is a property of a specific wire. Like this length of wire's resistance is 10. This length of wire's resistance is 15 ohms. So when we put this all together, resistivity goes up means more resistance. If the resistivity is big, it's a better insulator, so the resistance is higher. So here's your equation for wire resistance. We know it's directly proportional to length, so length goes in the numerator. It's directly proportional to resistivity. A better insulator means more resistance. So that goes in the numerator. And finally, we know it's inversely proportional to area. Having more area actually makes it easier for the electrons to flow through. So our final equation looks like this. It's got resistance is equal to rho times L over A. All right, so now that we got this equation, let's show you what you'd be responsible for in terms of using it. All right, so we know that the resistance of the wire depends on geometry of the wire. It depends on the material it's made of, the length of the wire, and the area, the cross-sectional area of the wire. Make sure in your notes that you put this equation here because you have open notes test anyways. Now, what you'd be expected to do is proportions. So let's say I have a wire whose resistance is, I don't know, 10 ohms. And let's say the wire looks like this. And let's say I asked you a question. What would happen if I triple the length while I double the area? Well, I know that tripling the length would make it harder for electrons to go through because they'd have to go through more distance. In traveling the farther distance, the electrons would encounter more other atoms, and each one of those collisions would slow it down a little bit. So in my new wire, it would have 3 times the length, but it would also have double the area. So I'm going to draw it just a bit wider. And that doubling the area would make it easier for electrons to get through. Doubling the area makes it easier for electrons to get through because it gives it more space. It's kind of like opening a second door when everyone's trying to get out of the cafeteria at the same time. So let's see what would happen here. The length triples, so that's 3L. The area doubles, that's 2A. Substituting into this original equation, I see that I haven't changed the material. I'm still using the blue marker, indicating that the material stays the same. So I have the same resistivity, same material, but triple the length and double the area. That means I get 3 halves times the original area. Rho L over A was the original. Since the original resistance was 10, 3 halves of the original resistance would be 15 ohms. The new resistor would be harder to get through than the old resistor because even though the area increased, the length also increased, and those didn't cancel out. So how about we try one more? We have rho LA, but you also in your lab know that the cross-sectional area is going to be a circle. When we make wires, it just makes sense to make the area a circle. It's easier to extrude the circular shaped wires than it would be to do weird things like, I don't know, pentagons. rectangular prisms. So when we model our wire as a cylinder with its area A and its length L and its resistivity, rho, we can also replace A with pi r squared, the area of a cylinder. So let's write this down in our notes. The other way you could write this is pi r squared, where r is the radius of the wire. So let's just do one more. Let's try a different proportion problem, but we'll use the green equation where we have the radius changing. Okay? Let's say I take my original wire and let's keep its original resistance as 10. Let's say we change the material. Let's say we make it a better resistor, a better insulator. Let's say we make a material that has twice the resistivity. So I've changed the material. I'm going to keep the length the same. But now let's have it double the radius. So now the radius is twice as big. And let's draw that out. Okay, now how would that change? In this case, I would see that the resistivity doubled. So I'd put in 2 rho for resistivity. The length was unchanged, but r doubles. And that r squared on the bottom means that I get a 2/4 times the original resistance. 2/4. So I have half of the original resistance. If the original resistance was 10 ohms, I have 2/4 of 10 was the original. So that is 5 ohms. Even though this material is a better insulator, the fact that you doubled the radius actually quadrupled the area. It made it much, much easier to go through. That's kind of like if you went on a highway and instead of having 1 lane open, you had 4 lanes open. Think about how much faster traffic would go. All right. Use all this information put together to solve homework 7.2, resistance and resistivity. Best of luck.